Howdy! Welcome to the Texas A&M 12th Astronaut Lab. Our project this year is the Scout Augmented Reality Visor design for NASA suits. Our team leads are as follows. Our advisors are Dr. Ana Diaz of the Bioastronautics and Human Performance Lab, Dr. Gregory Chamadoff of the Astro Lab, and our NASA advisor is Mr. Darren Welsh.
Background: NASA suits, spacesuit user interface technologies for students, challenges students to design and create spacesuit information displays within augmented reality (AR) environments. Students must develop an AR user interface that considers the needs of astronauts during the Artemis 2024 lunar landing mission. This includes planning for the extreme environment of the lunar South Pole. For humanity to explore space, we must apply the scientific method to expand our knowledge. The most difficult step is data collection, and it starts by actually getting to the moon and back. The Apollo program cost the US $25.4 billion, averaging $4.2 billion per successful mission. The amount of data collected per dollar is proportional to the efficiency of these EVAs. We can decrease collection time utilizing an AR device that aids the EV crew member in sampling, subsequently increase the number of experiments per mission, and further ensure the safety of the astronaut.
Here is the overview of the Scout AR program. Here are the system requirements for the NASA Suits competition. The user interface shall not permanently impede the astronaut's ability to perform. EVA task instructions shall be displayed. In case of an interruption, the astronaut must be able to continue the task on hand seamlessly. The astronaut shall be able to communicate with ground control at any time. The astronaut must be able to access the status of the spacesuit at any time. Also, a caution and warning system must be implemented to inform the astronaut about a spacesuit anomaly. The astronaut should know its location and how to navigate from one point to another at all times. The user interface shall take field notes for lunar sampling. With these design requirements in mind, our team has developed the Scout UI, which will be explained in more detail in the following slides.
Here's a high-level flow diagram of our design. The controls are powered by a wrist cuff, mixed reality toolkit voice commands, and HoloLens 2 hand gestures. The wrist cuff helps an EV crew member by adding redundancy to the controls. Hand gestures for long 6-hour EVAs may be tiresome for personnel. As you can see, these controls allow the astronaut to access and write important field data, display mission objectives, and increase spatial awareness.
This diagram shows the main features of our design. For the NASA Suits competition, we were asked to work on 4 main tasks involving science sampling, EVA system state, navigation, and auxiliary considerations. All the blocks with darker colors are the features we were able to implement, and the lighter colored blocks are the ones that we'll work on in the future. The main thing to note is that we're using the developer's whiteboard along with the learner repeater for science sampling, as well as including 3D models and holograms that can be controlled with voice on the HoloLens augmented reality system.
Hi, my name is Ashutosh Mishra, and I'll be presenting the design decision matrix. So in this section, we're going to be comparing 4 different interaction methods: the AR touch, the voice, the gaze, and eye tracking. And we're going to judge it on 3 different criteria and rank it a score between 1 to 10. And then we'll tally up all the scores and then compare to see which is the best interaction method. So going over these 3 different criteria: viability, like how likely is it to implement, how possible it is, how feasible it is, whether or not we can do that thing. Developmental cost, how much will it cost to produce to our design, how much from our budget will it take to build it and implement it into our design. And then finally, ease of use. How easy is it for the user to use the device? How easy is it for the user to become, acquainted with it, learn how to use it, familiarize themselves with it? So based off our results, we figured out that the voice was by far the best interaction method, and the AR touch came in a close second, whereas the gaze and eye tracking were far behind and can be neglected. Thank you. Now on to the next slide.
Hello, my name is Lauren Brady. Here are demos of the features in our Scout UI. We have developed many hologram features that the astronaut and the remote user, either mission control or an intravehicular crew member, can interact with. Seen in the first video is the astronaut interacting with the umbilical interface assembly. The astronaut is seen iterating through the procedure on the UI task panel and flipping the switches indicated. The switch holograms overlaid on the UIA panel animate what switches need to be flipped and show their correct position. Seen in the second video are the interactable box and arrow holograms. These holograms can be placed based on the procedure or by the remote user to indicate position or highlight certain items. For example, this video shows the user dragging the appropriate hologram off the UI panel and placing them into the view of the astronaut. These holograms can be manipulated and placed to indicate specific areas to assist the astronaut. In the future, the Scout AR assistant will be able to suggest and place appropriate holograms to the extravehicular crew member while they are completing an extravehicular activity procedure.
Our hologram compass is a compass that features points of interest set by the EVA or IVA crew. It shows distance and direction from the user to these interest points. This allows an independent astronaut during travel, as he will not need help during this period. The Lunarpedia is our field note journal that uses Azure Speech and Cognitive Services to transcribe the user's speech to text. This allows the user to be hands-free during work. The Lunarpedia also allows for photos and videos to be taken and uploaded for later viewing for other crew or mission control. The first picture shows an attached log, and the second picture below shows a sample photo with a quick description.
The Teleperson's Whiteboard is a tool used to assist crew members in the field with augmented reality drawings and holograms from a remote user. This use of live visuals allows quicker feedback for tasks and direction, leading to shorter EVA task completion times. In these videos, the HoloLens user's view is on the left, and the view from an IV crew member or mission control is on the right. From a laptop or VR headset, the remote user can see from the point of view of the crew member and provide instruction by drawing 3D splines. In this scenario, mission control is guiding the astronaut towards a waypoint in another room. In addition, the remote user is able to speak with the crew member, monitor the surrounding area, and help maintain complete situational awareness for the duration of the mission. This is all accomplished through a scan environment mesh sent from the HoloLens 2 over the Azure cloud, with multi-user replication using the Photon Engine networking library.
Our wrist control system is a physical control system for the HoloLens 2 using the Arduino Pro Micro. Signal between the HoloLens 2 and the Arduino is streamed via a Bluetooth module. Our wrist control system consists of 3 interactables. 1. A Bluetooth module for panel placement and adjustment. 2. 3 buttons for camera toggle, a main menu toggle, and a solver change toggle. Lastly, we have 2 3-volt batteries that powers our Arduino. The reason we provided our user with the wrist control system is so that way they can have an alternative way to interact with our UI that doesn't involve holograms.
Howdy, I'm Kevin Mayorga, and I will be introducing our research section. The main goal for the research team is to conduct research on human factors and to determine its importance to our UI design. The research team has been accomplishing this goal this semester by doing any necessary research for the tech team, such as conducting background research for navigation methods. The other main goal for the research team has been to conduct a study to be submitted in a journal in the future. The study we plan to conduct will test our adaptive navigation system. This system plans to be used to assist in navigation by creating and saving meshes with the HoloLens to serve as landmarks for EVA missions on the Moon. Lastly, the study will test the system in virtual environments such as the one shown of the Sahara Desert in order to test how well the system is able to scan different types of environments.
For our future work, our team plans on continuing studies for our adaptive navigation system. We plan on using virtual data from real environments for our initial tests. We also hope to test the system with the HoloLens in a real-life environment. Finally, we hope to eventually have volunteers to use the system in order to navigate a maze in virtual reality. We also have other projects we plan to work on, such as implementing 3D avatars in our remote telepresence system, testing our software with multiple HoloLens devices, adding a voice assistant with AI, as well as computer vision with deep learning capability. Thank you for watching our video. Do you have any questions? You can contact and check us out both at our website and our social media platforms. Our website is www.12thastronaut.com, and our social media can be seen on Facebook, Twitter, and Instagram at TAMU NASA Suits. Thanks and gig 'em!